All right, let's do some review and see if you're ready for the upcoming test. This is the 6.7 point review. In your big book, it's page 416 if you have this. All right, the first two examples are literal equations. This is a review of Math 1 that we wanted to have as a strong skill for us being able to switch variables and inverses and solve for the other variable. So let's go ahead and practice solving for x in these two equations. Anything that is around the x we need to get rid of to get x isolated or by itself. So we're going to start with subtracting 5 to move it over. 17 minus 5 is 12. And then we just divide by k. We just manipulated the equation to move things around to solve for x. How'd you do? All right, let's do the same thing to the next one. Here I want this x isolated. So I'm going to start by adding 2c to both sides, which gives me, and you can put this in either order. You can say k plus 2c or 2c plus k, doesn't matter. And then we divide by 9. Now you can write the whole thing over 9. So k plus 2c over 9 as a final answer, or you can split it up as k over 9 plus 2c over 9. It can be written either way. And remember, we're doing a multiple choice test, so you want to be prepared for both. Okay, so I'm just going to bubble both of these. Oops. All right, next one. Rewrite the formula given. Again, another literal equation for another variable. So what if I have a formula in terms of area, but I want the formula in terms of the base? I'm changing my perspective. I don't want an answer of area anymore. I don't have the base and the height, and I'm trying to get the area. Now I have the area and I have the height, and I want to solve for the base. So to move this equation around, in order to change it in terms of the b, we're going to start by getting rid of this 1/2. How do we get rid of a 1/2 in front? You could multiply by 2 or by 2 over 1. That leaves me 2a. This crosses out, is equal to b times h. And again, we're solving for b, so let's just divide by h. b is equal to 2a over h. How'd you do? Now it's asking us to do the same thing, rewriting this formula, but this time they want it in terms of the h. So here I go again. This time I'm going to multiply by 2, just like I did on the last step. But since I'm going for the h this time, I'm going to divide by the b instead. And we get h is equal to 2a over b. So look at the similarity between these two because we were going for a different variable. All right, let's try this next page. All right, if 3, -5 is an ordered pair of a function, which of the following must be an ordered pair of the inverse? So we're taking the 3, 5, and we're just completely switching the x and the y. So we're looking for -5, 3. And so that would be this guy right here. Now notice there's no sign changes when switching the variables. Okay, look at the next one. If 2, 3 is an ordered pair of the function, which of the following must be an ordered pair of the inverse? So we're going to take the 2, 3, and we're going to completely switch it, and we're looking for 3, 2. And there's our answer. All right, let's look down at these next ones. We're doing full inverses now. All right, first we're going to make it y equals x minus 10. We change the f of x notation into a y. Then we switch the variables. And then we solve for y. And y is equal to x plus 10. I'm going to switch that around so y is out in front, and then I put it in terms of inverse notation. What if I wanted to do this with the shortcut table method? What would that have looked like? There's literally only one thing happening where we're saying what's happening to x, it's being subtracting 10, and so we would say it's adding 10. So you'd write f of negative 1 of x is equal to, get your base x of ready, and you're adding 10. Check it out. Boom, boom. Do you like the shortcut table method, or do you like doing the switch of the x and the y's? Whichever method you prefer. Okay, I'm going to go ahead and switch this out for y. X is being divided by 6 and adding 3. So I'm going to switch x, put the y over here, and then I'm going to first subtract 3 from both sides, and then multiply by 6 to both sides. I'm going to switch it around and then put it with an inverse notation. And we're done. Again, you can do the shortcut method. Or you could say what's happening to the x, it's being divided by 6, and then 3 is being added, swoop it around, subtract 3, and times 6. Get that function ready. Start with a base of x, and then first we're subtracting 3, then we're multiplying by 6. Check out how they're the same. Which method did you like better? Last one on this page, here's number 5. Let's get the y equals before we switch the variables. Then we need to move things around to get y by itself. So let's start by minusing 7 and dividing by 3. So x minus 7 divided by 3, move it to this side, and then f of negative 1 of x equals x minus 7 divided by 3. Now, what's another way to write this, just so that I'm comfortable? I could say 1/3 x minus 7, where dividing by 3 could be shown as 1/3. I also could say 3 is dividing to both items here. So I could say x over 3 minus 7 over 3. All three of these answers are the same equivalent equation, and we need to be prepared for that because we're looking at a multiple choice test, and it could be in any three of those formats. What if we want to do the shortcut method for this one? First 3 is being multiplied, then 7 is being added. Opposite would be minusing 7 and dividing by 3, or you could say times 1/3. Let's go ahead and write that function, f of negative 1 of x. First, the base of x is minusing by 7, and then it's dividing by 3. Check out how this matches this and is equivalent to all these equations. Which method are you liking? Okay. The graph of g of x shown below has the same shape of the graph of f of x is equal to x, but it's shifted up by 3 units. Write the equation for g of x. So we take the base parent function, f of x is equal to x, and we apply the shifted up by 3. Remember that shifting up and down, the sign doesn't change or anything. We just say plus 3 to the entire function. Done. Oh, sorry, this is a g of x. Make that a g. All right, let's look at number 7. Parent graph is the regular parabola of x squared, but this has been shifted left by 4. So again, we're only seeing one change in these two. So g of x is the normal parent graph, but there's a shift left. So now we're going to go in the parentheses and a shift left. Recall that when we're in the parentheses, it's an opposite sign. Shifting left is x plus something. Shifting right would be x minus. So when it's inside the parentheses, there is a change to the sign. All right. This one down here is being shifted right from the original parabola, right by 5. So g of x is equal to, so a shift right or left happens inside the parentheses, and we need to remember the sign change, so right 5 is going to be x minus 5 squared. Finally, we've got an exponential function here. This exponential function has been shifted down by 2 from this original. So f of x, g of x, the new name, is equal to the original function shifted down by 2, and we're done. A down by 2 still shows up at the very end. No sign change needed. Okay, let's go take a peek at the next page. All right, the graph, original parent is x squared. We're now seeing 2 shifts to the original function. The x squared is going to be shifted right by 3 and down by 2. So g of x is equal to, we've got right by 3, so inside the parentheses, we've got right by 3, so inside the parentheses is going to be an x minus 3. Remember that the sign change happens inside the parentheses, and then down by 2 units. Notice the 2 shifts. Here's right 3, and here's down 2. All right, let's go try this guy. My original parent graph is shifting left 1 and up 4. And so we say g of x equals left 1 unit is going to be plus 1 squared, and then up by 4 is going to be plus 4 at the end. Now, if I was being asked to write the vertex of this parabola, can you take a second and write the vertex? See if you remember how to do that. Did you get that the vertex is negative 1 comma 4? Go check it out. Back 1, up 4. And let's go do this one. Did you get that the vertex was positive 3, negative 2? Check it out, positive 3, down 2. Remember that on these types of graphing problems on the test, you can use Desmos to double check. Double check that the graph that you're choosing is the equation that you're making. All right, let's look at the last one on this page, number 12. We've got a flip. It's being reflected over the x-axis and shifted down. When I see a flipped graph, when I see reflected over the x-axis, I'm thinking negative. There's going to be a negative in this equation, and our original parent was x squared. So here I go, g of x equals, there's now going to be a negative out front because it's flipped, and it's shifted down 3 units. So there's no change right or left, but there is a change of down 3 at the end. And from this, I can see that x plus or minus 0, comma negative 3 is my vertex, 0, negative 3 is my vertex. How'd you do? Okay. The graph of g of x shown below is the graph of x squared vertically stretched by a factor of 5. Vertically stretched by a factor of 5. Write the equation for g of x. So we take our x squared and we want something skinnier, so we want big number 5. That's the only change that's happening, a vertical stretch. So we want big number 5. The graph of g of x shown below is the graph of this horizontally stretched. Notice it's wider. So this word horizontally stretched means wider. This word vertically stretched means narrower. We made a little chart in our notes to remind us of that. So this is being horizontally stretched or wider by a factor of 3. When I see that, I'm thinking fraction of 1/3. When it's a horizontal stretch, it's a change that's happening inside or to the input. So I'm going to go, your x squared is now going to become 1/3 of x. So wait a second. Why is it inside the parentheses? Because it's a horizontal change, something happening to the input inside. Why is it 1/3 instead of 3? Because it's a horizontal stretch or a wider graph. When we have a wider graph, we know we want a fraction in that equation. Here's the absolute value function, the V-shaped graph. Same exact concept as what we just did. Horizontal compression is the same as vertical stretch. It's a narrower graph. So here's my narrower graph. And since it says horizontal, it's a change that's going to be happening inside the bars. So we're going to say g of x equals, and it's by a factor of 3. So that's it. Horizontally compressed, a narrower graph means I want an a value greater than 1. So there's my 3x. It's inside the bars because horizontal means a change to the interior input function. Finally, we have a vertical compression by a factor of 4. We know that vertical compression is the same as horizontally stretched. It's a wider graph, and it means I want a fraction in my answer. Because it's talking vertically, it's a number in front. It's not inside the bars. Horizontal is a change inside the bars or the parentheses. Vertical is just a change out front. Since we want a fraction, factor of 4, we're going to go 1/4 absolute value of x. And we're done. Again, use Desmos to check your answer to see if it verifies. Now, on this test, some piecewise functions pop up. Graph this step function in a coordinate grid, and then you're going to find it. So this is going to show up on your Apex test, and we haven't seen these since Unit 1. So today, in our review, I'm going to be showing you how to graph these on Desmos and how to input your domain. But what if you're in the middle of the test and you don't remember, or your Wi-Fi glitched out, or whatever might have happened? Then go type into Google how to type a domain in Desmos and read the directions on how to input this function. So I'm going to show you today how to do this, but feel free to Google it. How do I put in a domain into Desmos? So we're going to go graph this on Desmos together and see what it looks like, and then you'll find it on Apex. Same for number 18. I'm going to teach you guys how to graph this on Desmos, okay? And then find your graph. Okay, last but not least, we've got these two kind of word problems, application problems. How does the graph g of x equal to x plus 3 compare to the original graph of the parent linear function? So because it's just a plus 3 at the end, we're looking for a shift up. Shift 3 units to the right? Nope. That would be an x minus 3 in parentheses. Shifted 3 units up? Yes. This is my answer. Compressed vertically by a factor of 3? That would be a 1/3 x. So that's not my answer. Vertically stretched by a factor of 3? That would be a 3x. So that's not my answer. If you vertically stretch an exponential function, by a factor of 5, what's the equation of the new function? So down here we've got g of x is equal to 7 to the power of x, 10 to the power of x, 2 to the power of 5x, 5 times 2. Yeah, that's it. When I'm using exponents, I'm not going to be able to go 5 times 2 is 10, 10 to the power of x. And a vertically stretched by a factor of 5 means I'm going to multiply by the big number 5 out in front. There's my original function, 2 to the power of x. There's the big 5 out front. That's my answer. Now, over here on this blank page, I do want you to quickly make the table, just to refer to, of vertical stretch, vertical compression, and then horizontal stretch, and horizontal compression. Hang on, let me start this over again because you guys can't see the whole thing. Okay, so vertical stretch, vertical compression compared to horizontal stretch and horizontal compression. Okay, so real quick, vertical stretch is a skinnier or narrower graph. Okay, it has an A value greater than 1, so we're looking for a big number that is multiplying out in front. Okay, so you might have an equation like y equals 2x squared. You might have an equation like y equals 2 absolute value of x. Big number out in front, narrower graph. Vertical compression is the opposite. It's a wider graph where the A value is in between 1 and 0. And that means we're going to have a fraction that is multiplying out in front. So you might see something like y equals 1/9 x squared, or you might see something like y equals 1/9 absolute value of x, etc. Now, what are these horizontal things? They are literally the same way of saying a wider or a narrower graph, but it's the opposite word. Vertical stretch is the same as a horizontal compression. This is my narrower. Okay, so these two are the same. So my narrower is going to have an A value greater than 1 still. It's going to have a big number that's multiplying, except it's not out front. For a horizontal change, it's inside the parentheses with a change to x. So it's going to be inside the parentheses with a change to x. So you might see something like y equals parentheses 4x squared, or y equals parentheses 4x. Actually, sorry, I meant to put bars for the absolute value. There you go. So the change is going to be happening inside. It's still a big number A multiplying, but it's inside with the x when it says horizontal. Horizontal stretch, same as vertical compression. This is going to be a wider parabola. It's going to be when you see a fraction, because that A value is in between 0 and 1, just like this one. It's still going to be a fraction that's multiplying, but this time it's not out front. It's inside the parentheses or the bars. That is making a change with a change to the x. So what might that look like? It's going to be something like 1/4, oops, put that little x inside, squared, or 1/4 x inside bars. So that fraction is going to be inside with it. Remember that if you see something like this, 1/4 x squared, that quantity, it's really saying 1/16 x squared, because 1/4 squared is 1/16. That came up in our 6.5 quiz. Hope this helps.